And I'll refer to method 2 as either the LCD method or method 2. But I'm going to take the exact same expression. Okay, what you're going to do in this second possible method that you can use for complex fractions is you're looking to multiply the numerator and the denominator by the exact same quantity, and that quantity is the LCD of all fractions involved in the problem. So you're going to multiply the complex fraction by the LCD of every fraction in the whole expression. And then over itself. Okay, the whole point of it being over itself is any number over itself or divided by itself is a value of 1. So you can multiply an expression by a value of 1. It's called the identity property of multiplication without changing its value. So what we're going to do is we're going to, again, look just in the numerator and then just in the denominator. So notice as I kind of break these pieces, I will use brackets and grouping symbols to indicate what's in the numerator or what's in the denominator. I'll also write in a denominator if it doesn't already exist. So an over 1 will be used anytime there's not an actual fraction in the expression. So if we go through and we find the LCD of all the fractions, so we need a 1, we need a y, and we need a 1. So our only LCD factor is a y. And now, does everybody see that even though y squared is in the denominator of the complex fraction, when we look at the individual fractions, here it's not in the denominator, it's in the numerator of that individual fraction. So we're going to multiply the top and bottom by this number over itself. And then basically what you're going to do right here is you're going to work just in the numerator and then just in the denominator, and you're going to expand each of these. Okay? So the second step is to expand the numerator. So if we distribute our LCD to both of the fractions in the numerator, y times y over 1 gives you a y squared. Y times x squared over y, well, what's going to happen to our y's here? They cancel, leaving just the x squared. So we simplify our numerator into a single expression with no fractions now. And we're going to do the same thing in the denominator. So in the denominator, we're going to expand. So here, we're going to take our LCD factor, and we're going to multiply it to every term of our denominator. In this case, we just have this single term. So y times a y squared over 1 gives you y cubed. And then your final step here is to reduce. So as we simplify and reduce this, we can rearrange the terms. X squared plus y squared can't be factored at all over y cubed. We have our simplified form. And so do you see how in this particular case it wound up being faster? A little bit more efficient. Okay, so the advantage to this method is in the right situation it's much more efficient. Right? However, the right situation is basically if the LCD of every fraction is limited to 1 or 2, maybe 3. This method is probably more efficient. Once you get to, if there's 4 different LCD factors, don't use this method. It will wind up being more complicated than it is time saving, and so it's not worth it in that case. So if you have 1, 2, or 3 LCD factors, but even 3 may or may not work, but 1 or 2 for sure, this second method is much quicker. Now the disadvantage to this is finding the domain restrictions, because the domain restrictions aren't going to show up as being canceled out in the process. So you have to make sure if you use this method that you find the domain restrictions. of the original form. And you have to go back in the original form and look to see y can't be a 0. Here y can't be a 0. That's the only restriction that the original form identifies. Is that apparent in the simplified form? Yeah, so you don't need to include it separately, but this step needs to be accounted for. And for the LCD method, again, we're still kind of treating the numerator separate from the denominator. But this time we're going to multiply by the LCD of every fraction in the whole problem. So we have an x minus 1. We have an x plus 1. We have an x minus 1, which we already have, and an x plus 1, which we already have. So here's our LCD. Once you find your LCD, and you're just going to list all the factors in your numerator, once you find that, you're going to duplicate that in the denominator. So again, you're multiplying by a value of 1. But we're just going to work in the numerator separate from the denominator. So let's work in the numerator, distribute through. So here when we take this first fraction, x over x minus 1 times this LCD, the x minus 1's cancel, so we're left with just the x times the x plus 1. When we distribute to the second fraction, the x plus 1's cancel, so we're left with a negative x times the remaining factor, x minus 1. So that's all that's left in our numerator when we distribute through. We're going to move to our denominator and do the same thing, distribute through. Distribute our LCD to both fractions here. The x minus 1's cancel, leaving an x times the remaining factor, x plus 1, plus here the x plus 1's cancel, we're left with x times the remaining factor, x minus 1. So that's all that's left in my denominator after I distribute through. And so now it's just a matter of simplifying. So as we go through to simplify this, distribute our x, giving us x squared plus x, minus x squared, minus a minus becomes plus x. All over here, do the same thing. We get x squared plus x squared minus x. And as we simplify, x squared minus x squared cancels, leaving a 2x. Here the x and the negative x cancel, leaving a 2x squared. We cancel, the 2's cancel, the x cancels with one of these x's, and we're left with 1 over x. Okay, so advantage here is it's quicker. Disadvantage is when you look here, these were individual terms being combined, so they're not factors being canceled. You don't see any canceled factors other than this right here. So you know x can't be 0. That's apparent in the simplified form. So what you have to do is you have to go back in, look at every denominator, every factor in the denominator of your original form, make sure those restrictions are identified. So here x can't be a 1. Is that identified in our simplified form? No, so we would need to include that. So x can't be a 1. Here x can't be a negative 1. Is that identified in this simplified form? No, so we need to include negative 1 and 1. And those are the only two restrictions. And so you have your simplified form with the built-in restrictions, or with the additional restrictions. Okay. And the method that I would use on something like this is the second one. Because if I looked at this, what I would see is, again, if I look at each of these individually, I have an LCD factor of 1, x, and a second x. So my LCD is just x squared. X squared, x, 1. There's nothing additional to that. And so the LCD method, or the second method, allows me to just take x squared over itself and multiply the top and bottom by each of those individually. So if I distribute my LCD to each term in my numerator, I have 1 times x squared is x squared. Here, one of the x's cancels, so I'm left with minus 5 times the remaining factor x. Here, the x squareds cancel, so I'm left with just the minus 24. So there's my numerator. Now, if I work in just the denominator here and distribute my LCD to all three terms, the x squareds cancel, leaving just a plus 15. Now notice, I'm going to rearrange my terms so that they're written in standard form as I do this. One of the x's cancel, so I'm left with a plus 8x. And then here, nothing cancels, so I'm left with an x squared. So I've reduced my complex fraction into just a single fraction. And now I can look to continue reducing here. I have binomial factors First term's x. The second terms are the two factors of negative 24 whose sum is negative 5. So negative 8 and positive 3. In the denominator, again, I can find binomial factors, x and x. My two factors of positive 15 whose sum is plus 8 is plus 5 and plus 3. I can then cancel my common factor, and I'm left with my answer, x minus 8 over x plus 5. Now notice, I used that second method, and I did find that there are... So I used that second method, and I did find that there are some factors that got canceled from the denominator. So I do have to restrict this. I know that x is not equal to negative 3. However, because I used that second method, I have to go back in, look at all the denominators of my original form, make sure none of those denominators' values can ever give division by 0. So what else do I see x can't be? 0. So I need to include the restriction x is not equal to negative 3 and 0.